David Hysi from the Institute of Sustainability and Civil Engineering from RWTH Aachen. Please, the floor is yours.
So, my name is David Hysi and I'm a doctoral researcher at the Institute of Sustainability at RWTH Aachen. I'm going to be presenting the work of Pamela Haverkamp, my former colleague who did the most of the work in the first phase. So, as we already know, digital twins are increasingly being explored in road infrastructure, but mainly for three reasons: to optimize design, for asset management, and for predictive maintenance. However, current sustainability assessment methodologies do not capture the full impacts of the digital twin role, because they are still very centered on the physical assets, so material production, construction, and maintenance, but neglecting the digital components and the operational energy and water use that is needed throughout the use phase. And even when sustainability shows up in the digital twin, they are mostly treated as enablers of the assessment, so they can provide data availability, real-time assessments, and scenario analysis, while neglecting the sustainability implications of the digital twin itself. So what comes from the sensors, data infrastructure, and the operational energy. And also we don't know the full sustainability parameters that need to be addressed. So for those who are less familiar, what is sustainability assessment? I'm referring to life cycle sustainability assessment, which is a methodology that evaluates the sustainability performance of a product system throughout their entire life cycle, covering the all three dimensions of sustainability across equivalent system boundaries. So we are talking about the environmental aspect that is assessed through LCSA, that assesses the potential environmental impacts of a product system from raw material extraction to end of life. The economic one through LCC that covers and checks the cost from the perspective of particular stakeholders, being road agency, contractors, and users. And the social, which is the one who addresses the positive or negative social impacts across life cycle of products from the perspective of different stakeholders, being workers, local communities, value chain actors, children, and society. In addition, the other pillar is also criticality. Criticality assessment refers to the importance of a resource within the system. So we can use it to identify what are the main materials that are quite crucial to the system, to then later focus the LCA on that. So how can we further develop the life cycle sustainability assessment frameworks to capture the digital twin roles? First of that is to adopt the product system by conceptualizing and expanding it to consider three elements. First element is the physical road system, which is the normal assessment that we currently do. And it covers, for example, the road pavement structure, the road pavement materials, and the auxiliary elements of the road structure. The second one is the digital road system, which comprises of all the hardware and infrastructure required to create, operate, and maintain the digital twin of the corresponding system, and the operational feedback mechanisms, which are the elements that enable data-driven interventions. So, sensor data flows from the physical road system to the digital road system to then create predictive insights that fit to the feedback mechanism that can then trigger potential interventions to the physical road system. The second is a functional unit. So functional unit, for those who are less familiar with it, is the quantified function of the product systems to which all the inputs and outputs are related to. So the introduction of the digital twin does not alter or make a different functional unit, but we come to the need that it needs to be expanded. So normally, how we define a functional unit is about defining the road type, geometric characteristics, expected load, traffic, performance requirements, and the service side. With the inclusion of the digital twin, there are also other performance-related parameters that we need to consider, such as, for example, the International Roughness Index, routing resistance, and skid resistance, and not to forget also the lifespan that is added through the digital twin that can enable like condition-based maintenance, can reduce unplanned interventions, and can thus extend the lifespan. The second is the system boundary. What shows up in the system boundary with the inclusion of the digital twins is that the modules B6 and B7, which are about operational water and energy use, becomes mandatory because we have a lot of digital components that need to be operational throughout the lifespan of the road. So we need to be considered also about the impacts that arise from these phases. Going back to the life cycle assessment, what stands out apart from the normal impact categories that we need to consider, that are impacts arising usually for material production, is also the impacts that can arise from the electrical grids, especially in systems or countries where there's a lot of share from fossil-based generation, such as currently Germany. Then we have additional impact categories that we need to consider in the overall LCA assessment. When it comes to life cycle costing, NCC net present value remains still applicable for the digital twin. However, we need to consider also like the cost from the sensing data, data processing, software, and operational energy use throughout the life cycle of the infrastructure. Now, this cost may be offset because like we can reduce operational costs throughout the life cycle of the structure. However, this needs to be quantified in further research. On the social aspect, we can identify relevant social issues by conducting a social risk assessment that can generate and can reflect geographical and sectorial conditions. From our work, material production was where most of the social impacts were coming from, but the introduction of digital twin introduces also new social considerations, such as, for example, the social acceptance that emerges as an important topic that needs to be discussed because it affects also the how people approach and how this technology develops. The difficulty here is that the lack of primary data. Like, to do an actual social impact assessment, there's the need of primary data regarding to the infrastructure. When it comes to the criticality assessment, it is quite a useful tool to be used as screening because it can identify materials and components whose disruption could disproportionately affect the system's performance. And with that, we can use it to find possible trade-offs between criticality and sustainability performance. So to conclude, the introduction of digital twin does not alter the product system. However, digital components directly influence the operation and maintenance phase. Future RED sustainability performance will account for the physical assets, the impacts of digital infrastructure, and the operational feedback mechanisms. The functional unit does not change, but it needs to be expanded to account also for the different elements that are part of the digital twin. The operational energy and water use are essential and they need to be accounted for. And prioritization of impact categories reflects both continuity and also change from the conventional roles. So criticality assessment still needs to be complementary, but it addresses risks that are not fully captured by life cycle sustainability assessment indicators. And if there's a take-home message, that digital twins require further development of LCSA framework to extend established parameters and capture the full characteristics of the cyber-physical system. So this work is going to still proceed in the second phase of the SFP and sub-project CO2, where we're going to expand the framework to account for future environmental, social, and economic impacts. So, with this, thank you.
Yeah, thank you.